right, hello and welcome to Office Hours, first Office Hours of the week. As always, I'm here to answer any and all of your questions. And if you have, if you're here and you're live and you have questions, oh, awesome! Here we go. All right, so Victoria, let's see. Okay, lab number 4, question 8. Okay, quick question. All right, let's see. So quick question, is this Chem 400? Because currently there are several I have several lab 4s in the mix between all the classes that I'm teaching. Okay, solid. So let me pull it up. All right. So, all right, so for, this is Chem. There we go. So let's see, you had lab 4, question 8. Okay, let's see. On the basis of the reactions observed in the 6 test tubes in this experiment, explain why the position of hydrogen cannot be fixed exactly with respect to all of the other elements listed in the activity series. In question 6, use experimental data and explain your observations to explain your answer. Okay, so confused on how to answer it. Okay, so I guess my first question So Victoria, my question to you is, do you understand what they're asking in this question, but you're not sure how to articulate it, or are you unsure what they're asking in the first place? Okay. All right. So basically, with this, so this problem's about the activity series, right? And what you're doing in this experiment is you're comparing. Okay, okay, awesome, Victoria. That helps me a ton, a ton. So the deal is with this with the whole reactivity series, you're looking at so for example, um, you're you're looking at a whole range of metals and what they react with, right? Um, so, for example, if you had um, solid cobalt, for example, and you're mixing it with aqueous gold chloride, for example, and you get no reaction, the products for this reaction would have been solid gold and aqueous cobalt chloride, but those didn't form. What that tells you is that when you compare the two ions in this reaction, you're comparing gold. One is your cation, right? Sorry. So when you compare the two metals, sorry, it's my 2-year-old who's on his way to nap time, which is never fun. We're comparing cobalt versus gold. All right. And because there was no reaction, that tells you wait, hang on, that tells you that gold is more reactive than cobalt. All right. If there had been a reaction, then cobalt is more reactive than gold, but because there's no reaction, gold is more reactive than cobalt. And so they give you a series of these things to kind of make an activity series to rank things as to which one's more reactive, which one is less reactive. And what problem 8 is asking for in question 8, they're asking why can't you rank hydrogen's reactivity? Based on your experimental data. So in other words, another way of thinking about this question is what data, what experiment, rephrase it that way. What experiment would you need to do to determine hydrogen's reactivity? In this experimental activity series. Because basically what this problem is saying is they didn't give you enough information to determine exactly where hydrogen would fall in your activity series, whether it be more reactive than this, less reactive than this. So probably the most effective way of answering this question is by answering this kind of rephrasing, restructuring of the question, which is what experiment would you need to be able to determine where hydrogen fell on the activity series? Does that make sense? So Hannah, I'm assuming that you're asking about redox reactions. Totally. Yes, we can definitely do. We can definitely do some problems like that. Okay, so let me cook up an example. Okay, so let's see. Write a balanced chemical equation for the following redox reaction. That takes place in acidic media. I totally can. This next example is 100% exam caliber. So yeah, this one totally material you could see on the exam. All right. So let's see. Let's do. Okay, so let's do a reaction between. I'm coming up with this on the fly, so I'm just making sure that everything will add up. Totally. All right, so let's do a reaction between aqueous sulfuric acid and sorry, hang on. I think I gotta silence my phone. Sorry about that. Okay. Oh wait, hang on. I started writing this in the wrong layer. So this is aqueous, and this is going to make SO2 gas. And we're going to react this with solid nickel. And we're going to make aqueous nickel to cations. Let me just make sure that everything adds up. Okay. Okay, so cool. So this is the thing. Let's go ahead and write a balanced chemical equation for this reaction that takes place in acidic media. Now, what we want to keep in mind is we're going to be using the half reaction method to solve this problem. So the half reaction method, in the half reaction method, we start by splitting our reaction up into two half reactions. All right, this will be one half reaction will be the reaction of nickel going to nickel 2. The second half reaction will be sulfuric acid going to sulfur dioxide. After you split into your two half reactions, then step 1, you balance your atoms for each half reaction. Step 2, you balance your charges. Step 3, you balance your electrons, and then you recombine your two half reactions. And that is, those are the 5 steps for balancing redox reactions. So our first move is we need to split this reaction up first into a reaction where solid nickel becomes aqueous nickel 2 cations. And then the second half reaction is one where sulfuric acid becomes sulfur dioxide gas. All right, that is step number 1. We split our reaction into two half reactions. Now we need to balance our atoms and our charges in these two half reactions independently of each other. Let's go ahead and, whoops, I actually want to start with my nickel half reaction. So first off, we need to balance our atoms, and you'll notice that there is one atom of nickel on either side of this reaction, so it is totally balanced as far as atoms are concerned. So our atoms check out. Now we need to look at the charge on each side. The charge on our reactant side is 0. The charge on our product side is a positive 2. So our charges are imbalanced, and the only tool we have at our disposal for balancing charges are electrons. We can add electrons to either side of this reaction to even the charge situation out. Electrons are negative, so we can only make a side more negative. We need to bring our positive 2 charge down to 0 if possible, and it is possible if we add 2 electrons to our product side, because positive 2 minus 2 is equal to 0. So now charges are balanced. So we balanced atoms and charges for our nickel half reaction. Let's go ahead and look at our sulfur half reaction. I'm actually going to move this just over a little more central. All right, first off, we have to balance our atoms, and that is going to take some effort. So we have hydrogen, sulfur, and oxygen. On our reactant side, 2 hydrogens, 1 sulfur, 4 oxygen. On our product side, we have no hydrogens, we have 1 sulfur, and we have 2 oxygens. All right, now, step number 1, whenever you are balancing a redox reaction and oxygen's out of whack, you always start by, you balance your oxygen count with the addition of water. So we're going to add H2O to our product side, and we need to add 2 water molecules so that we get a total of 4 oxygen on the product side. The addition of our 2 water molecules also adds hydrogen, so we're adding 4 hydrogen to the mix, and now our hydrogen count is out of whack. Right, we have 4 on our reactant side, but only 2 on our product side. Now, we're in acidic media here, so the way you balance hydrogen when you're in acidic media is by adding H plus ions. Specifically, we need to add 2 H plus ions so that our hydrogen count balances. So now we have balanced atoms on both sides of this equation. And I need to write in plus 2 water molecules plus 2 hydronium ions. All right, this hydronium's aqueous, water is a liquid. All right, so now our atoms are balanced. Now that our atoms are balanced, we need to look at charges. We have a total charge of +2 on the reactant side and a total charge of 0 on the product side. Product side. +2 on the reactants, 0 on the products. We need these two to be equal, and you can only balance charges because by adding electrons. So we need to add 2 electrons to the product side because -2 + 2 equals 0. And now our charges are balanced. There it is. Okay. So at this moment in time, we have balanced our atoms and our charges both for both half reactions. Now we need to balance our electrons. So let's go ahead and bring in our nickel half reaction, which had solid nickel metal, producing nickel 2 cations, which are aqueous, plus 2 electrons. And so actually, and this just worked out this way. I literally made up this problem on the spot. You have to make sure whenever you're, and you'll see what I'm talking about when I said this just worked out. Whenever you're balancing a redox reaction, you need to make sure that the number of electrons produced by the oxidation half reaction equals the number of electrons consumed by the reduction half reaction. I don't want to say what is usual or not. These won't always be the same number, so you have to make sure that they are. So you have to multiply one reaction by a number so that the electrons consumed equal the electrons produced. Here, they're both equal, so we don't actually have to do any unit multiplier. We can just add the reactions together as is. So our 2 electrons on the product side of one half reaction cancel, the 2 electrons on the reactant side of the other half reaction. So this ends up being 2H+, so 2 hydronium ions, plus sulfuric acid, plus solid nickel produces aqueous nickel plus sulfur dioxide gas plus liquid water. So this is actually the balanced redox reaction. And again, I made this one up off the top of my head. I didn't mean for the electrons to just work out perfectly. I can totally do another one if you want to see one where the electrons don't work out perfectly, as they did in this case. That was just pure coincidence. So let me know. Yeah, totally. Or total. Okay, yeah. Let's do one. Let's do one in basic media. Oh, I put all of that in the same layer. All right, let's do another example. This time, this one will be in basic media. Okay, and let me. Okay, right. I'm gonna do. Aqueous bromate reacting with aqueous manganese 4 oxide to produce permanganate and bromine. All right, and this will be in basic media. So the first thing that we got to do is we have to split this half reaction up. One of the half reactions will be the reaction between, or bromate, bromate becoming bromine. The other half reaction will be the reaction in which manganese 4 oxide becomes permanganate. Okay, I was just making sure that everything's going to work out. And it will. Okay. So let's go ahead and dive in. We'll handle the bromate half reaction. Or no, we'll do the manganese half reaction first. So we'll do MnO2 which is aqueous going to MnO4 All right, now first step, we got to balance our atoms. So we have manganese and oxygen at this moment on both sides of this reaction. We have 1 manganese and 2 oxygen on the reactant side, 1 manganese and 4 oxygen on the product side. Now, we got to balance oxygen. The only way to do it is by adding molecules of water. We need to add 2 of them so that we get a total of 4 oxygens on the reactant side. Now, this introduces 4 hydrogen atoms to the reactant side. Now, when you're in acidic media, when you're in acidic media, what you do is you add H plus, right? So if this was acidic media, we'd go +4 hydronium ions and we'd be good and we'd be done. You do the same thing. You do the same thing when you're in basic media, except you can't leave that H plus there, all right? You can use it to balance, you can use it as a placeholder, but you can't leave it there because H plus is hydronium. That's produced in acidic media. Basic media produces hydroxide. So to undo this effect, you need to add however many H plus ions you add. You have to add that many hydroxide ions to both sides of this equation. And the reason why you must do this is because of the following neutralization reaction. All right. One ion of hydronium will react with one ion of hydroxide to produce one molecule of water. All right? And so because we have 4 molecules of hydronium reacting with 4 molecules of hydroxide, this is going to produce four molecules of water. All right, so this changes up our equation. Now we have 4 ions of hydroxide plus 2 molecules of water plus manganese 4 oxide producing permanganate and 4 molecules of water. Now you'll notice that we have H2O on both sides of this equation, so we can cancel. These 2 water molecules will cancel 2 out of these 4, so our final manganese half reaction will be 4 hydroxide ions reacting with manganese 4 oxide to produce permanganate and 2 molecules of water. All right, now here's the crazy thing. That felt like so much work. We've only just finished balancing the atoms for this half reaction. Right, when you look at, okay, what have we accomplished? We've just balanced our atoms. We still need to balance our charges. So let's go ahead and do that here. When you look at the charges on our reactant side, we have 4 negative ones, right? 4 hydroxides. When you look at the charge on our product side, we only have 1 negative. And we need these 2 to be equal. All right, now the only means that we have to manipulate charges, just making a little more room here on the end, is we can add electrons. we can only make a side more negative, so we need to make our -1 equal to -4. We can do that by adding 3 electrons. They'll add an additional 3 negative charges, and now our charges are balanced for the manganese half reaction. So we have our manganese half reaction locked and loaded, ready to go. Let's take a look at our bromine half reaction. So our bromine half reaction is going to be BrO3 bromate becoming bromine. I'm going to move this to the top of our page. Step number 1, we got to balance our atoms, right? We got to balance our atoms. And on our reactant side, we have bromine and oxygen, 1 bromine, 3 oxygen. On the product side, at this moment, we only have 2 bromine. Step number 1, we got to multiply bromate by 2 so that we have 2 bromine on both sides of this reaction. This is going to increase our oxygen count. Next, we have to balance our oxygen atoms. You can only balance oxygen with the introduction of water, and we're going to bring in 6 water molecules so that we have the same number of oxygen on both sides. Now, doing so will also introduce 12 hydrogen atoms. In acidic media, we would balance this hydrogen situation with the introduction of 12 hydronium ions, which is fine. We can add it, but we can't leave it in the equation because we're under basic conditions. Hydronium isn't free-floating in solution. Hydroxide is. So what do we do now? Well, we have to undo what we've done. For each hydronium ion, we need to add a hydroxide to both sides of this equation. These 12 hydroxides combine with 12 hydronium to make 12 molecules of water plus 2 molecules of bromate and they produce 1 molecule of bromine plus 6 molecules of water plus 12 ions of hydroxide ions. Some of our water molecules can cancel. The 6 water molecules on our reactant side will cancel with 6 of them on our product side. And so our bromine half reaction with balanced atoms will be 6 water molecules reacting with 2 bromate ions to produce 1 bromine molecule plus 12 hydroxide ions. Atoms are balanced. Let's look at our charges. On the reactant side, bromate has a charge of -1. We've got 2 of them, so that's a total charge of -2. That's the reactant side. On the product side, hydroxide has a charge of -1, but we have 12 of them for a total charge of -12. Now to balance our charges, we got to use electrons. We need our reactant side to become more negative. So we're going to add 10 electrons because negative 10 minus 2 is equal to 12. And now our charges are balanced. Whew. All right. Charges are balanced. Next, we need to balance our electrons. Balanced atoms, balanced charges. Next, we need to balance our electrons. So I'm going to rewrite my manganese half reaction here. 4 hydroxide ions. Plus manganese 4 oxide produces permanganate, water, and not 2 electrons, excuse me, 3 electrons. All right. Our second half reaction is six molecules of water plus 2 molecules of bromate produce bromine, 1 molecule of bromine, plus 12 molecules of hydroxide. Shift this over. Because we also have 10 electrons on the reactant side of this half reaction. Now, to balance electrons, we need the number of electrons being produced by the oxidation half reaction to equal the number of electrons being consumed. Yeah, totally. We got to have that there. Now we have to have the same number of electrons on either side. Right now we have 10 for the bromine half reaction and 3 for the manganese half reaction. 10 and 3 don't go into each other evenly. So we need to take the manganese half reaction, multiply this by 10. We need to take the bromine half reaction and multiply. Yeah, no worries. Hannah, that was a great catch. It was an excellent catch, and it shows that you're dialed in to this problem, which is probably the hardest problem in Chapter 4, at least for many students. This is the hardest type of problem in Chapter 4. All right, so we multiply the bromine half reaction by 3, the manganese half reaction by 10. Numbers are going to get gnarly, but we can hang with this. So multiplying everything in the first reaction, half reaction by 10, we get 40 hydroxide ions plus 10 manganese 4. Lots of work with basic media. Yeah, exactly. It's way more work when you're in basic media. When I was a student, I always loved seeing acidic media problems because I knew they were easier. Easier by default. So that's 10 permanganate ions plus 20 water molecules plus, this is the whole reason why we're doing it, 30 electrons. That is a lot of electrons. The bromine half reaction, when we multiply everything by 3, we start with 30 electrons. Plus 3 times 6 is 18 molecules of water. 3 times 2 is 6 bromate ions, producing 3 bromine molecules. Plus 12 times 3 is 36 hydroxide ions. All right. We have made it all the way to the recombination step. I'm just going to move my 2 reactions up to meet each other. Scoop that one over there, and we'll scoop this one over here. Whoa. All right, that's about as good as it's going to get. Let's go ahead and add these 2 up. Now, several things are going to cancel when we add these 2 together. Namely, so specifically, we have 18 water molecules on the reactant side for the bromine half reaction. We have 20 on the product side for the manganese half reaction. So this 18 will cancel all but 2 of these water molecules. Another species that's going to cancel is hydroxide. We have 36 on the product side of the bromine half reaction. We have 40 on the reactant side of the manganese half reaction. So 36 will cancel all but 4 of these. All right, now let's go ahead and do this. Let's see, does anything else cancel? Oh yes, one last thing does cancel, and it's arguably the most important thing, the whole reason why we're doing this. If you've done your job right at this stage, all of your electrons should cancel. So 30 electrons, cancel 30 electrons. If they don't, that tells you that something you did in a previous step went wrong. So that means go back, figure out where things went wrong. It can help you avoid mistakes. So let's look at what's on the reactant side. We have 4 hydroxide ions plus 10 manganese 4 oxide molecules plus 6 bromate ions produce, let's see, 10 permanganate ions plus 2 water molecules plus 3 bromine molecules. Feels a little bit like or feels like a bit of a bloodbath, but that is the final balanced redox reaction. This thing's full metal. This is as rough as anything that I'd put on the test, and not everything on the test will even be this level of difficulty. So this is a great example problem. Dude, you're so totally welcome. I'm stoked that it helps. Honestly, with many things in chemistry, redox especially, it's really just a matter of repetition, and the more you can like kind of churn through problems, work through it, the more it starts to make sense. Um, I think often with problems like this, they can be scary right at first, and so at times people can be avoidant of them, but then that just kind of snowballs. Dude, you too. Totally. Anytime. Absolutely anytime.